Engineering 305, example problem 820. We're going to solve with cartoons this time. And honestly, I'm just making algebra mistake after algebra mistake after algebra mistake, and I'm frustrated. I'm frustrated, and so it's these are hard. These are hard, not because they're hard. They're simple, but because you make stupid mistakes, and so you've got to pay attention to all the little details, and you've got to constantly monitor things. But anyway, let's get after it. So, same problem that I just did several hours ago. Same green shirt, if you notice, and we've got a beam, we've got it loaded and supported. We want to figure out the reactions at A and B. Okay. The problem with that is if we draw that, right? I draw that beam and I've got a reaction moment here. I've got a moment at A. I'm going to give it blue just to I've got a reaction at A and I've got a reaction at B, and then I've got this distributed load. So you're trying to find the reactions. There are 3 reactions, and I have 2 equations, right? That's the fundamental of statically indeterminate. Is I'm going to get rid of that because I'm writing down free body diagrams. I got sum of the forces in the y direction equal RA plus RB minus W times the length, which is, here's we got to be careful. It's 5/4 L long, and there's equation 1. And then I've got a second equation, sum of the moments, and you can pick any spot to put them. Got a preference? I like going around the origin, using the same beam. Oh, sorry. That's an equal to 0. This is the moments at A are going to be minus. The moment at A is creating it to go the wrong way. The reaction at A goes away. I've got the distributed load is going to cause it to go the same way that the moment at A does. So that's a minus W times the length of the weight. And then the distance at which that's applied is actually 5/8 of L. And then lastly, I've got the reaction at B. That's the only thing causing it to go the other way. So that's a plus RB, and then the length, the way that it acts. And there I got that. So now, there you go. 2 equations, 3 unknowns. So I need to find one more equation. And here's where we take the force at B and we say we don't know what that force at B is. Well, we really don't. It's a variable. But we know an extra boundary condition that has the deflection. I know that. The deflection at L at B is equal to 0. So now we want to write that equation using the cartoon method, using superposition and the cute pictures we got. And so the first thing I'm going to do is I'm going to break this problem up into, I've got a cantilever beam with a distributed load, and I'm going to add to that plus a cantilever beam with a load at the bottom, and I know that the deflection at L is equal to 0. So there you go. Now, do we have equations for those 2 things? Yeah, they do. They come right out of, I'm going to pull them up. They come right out of there. So we've got the simple cantilever beam as load case 1. We've got a point load at the end. Now you got to remember, my lengths are all changing, so we've got to be careful when we use these symbols to make sure that our lengths, our X's, our L's, our P's, our W's all match up with what this is thinking. So we've got to be careful. I've got case 1 for the point load, case 2 for the distributed load. So let's start writing these things down. Excuse me. All right. Oh, I turned on the picture again. There you go. So for this situation, what we have to pay attention to is the length of the beam is equal to 5/4. The length, in quotes, length, right, is equal to 5/4 L. And where I'm interested in the deflection, X, is not at the end, but it's equal to L. And so I'm going to use that I'm going to use the equation at the end, all the way at the end, the equation of the elastic curve upward, where it's giving me the deflection as a function of x. All right. So I'm going to write that down behind the scenes, but what we're looking at is that deflection is equal to minus, because that weight is pushing it down, so it is going to be a downward deflection, w x. I'm going to write it in their variables, and then we'll convert it to ours in a sec. X squared over 24EI. And then we have this quantity in the bracket, x squared minus 4LX plus 6L squared. All right, that's the one term. So I've got that written down here. That's this part. And then I'm going to put a giant plus. And now here's the cantilever beam section. Now for the cantilever beam, I'm actually looking at L, the distance L away. So this X is equal to L. Or if I go back to my equations, I can just look at the maximum deflection upward and use the middle, which is that. And now I got to be careful. Minus PL cubed over 3EI. But my force is going up, so my deflection's the other way. So it's actually P, which is, I'm going to write it that way, PL cubed over 3EI. And in this case, P is equal to RB. And L is equal to L. Anything else I got to know? So P is equal to RB, L is equal to L. I guess I should say W here, the distributed load, is equal to W. Okay, now let's substitute in. The deflection at L is equal to 0, not at 0. Oh, watch. Put that back. Del at L equal to 0 is equal to minus W stays that. X is equal to L squared over 24EI times X, which is just L squared, minus 4L is 5/4 L, and then X is equal to L. Okay, if that's a little confusing, I understand it. It is. And then plus 6 times L squared. L is equal to 5/4 L, so it's 5/4 quantity squared, L squared. Okay, that's all that first term. Plus RA. L is equal to L over 3EI. And that whole expression is equal to 0. And now you're going to see, actually, I'm going to be able to solve this one equation in terms of RA. RA will be in terms of W, which was a given. And so then I'll be able to go back to the other equations, because I'll have two equations and only two unknowns. Sorry, that's not RA, that's RB. I'll have RB or I can solve for RA and the moment at A, because I'll have eliminated RB as a variable. So, all right, let's plug away here and figure this out. Minus W L. You see, this has L squared throughout the whole thing. This expression. So I'm going to just make that WL to the 4th over 24EI. And then we'll start dealing with this on the inside, which is a 1 squared. I can do that. I didn't make any mistakes on that. Minus, the L's are gone, the 4's cancel, minus 5, plus 6 times 5/4 squared. Oh, that's ugly. Maybe it's not that ugly. Fine. Plus RBL over 3EI. I'll put the 0 back over there just to be complete. All right, let's plug away. Well, somehow didn't like that. Wow, that was kind of weird. Okay, got her back. I actually, well, let's keep plugging. I'm going to rewrite this minus WL to the fourth over 24EI. I can see this term on the end is going to give me a 4 squared, right, on the bottom. Or I could just rewrite that as a 16, but either way. And so this is going to be 16 sixteenths. This is going to be 80 sixteenths, 5 times 16, 80, plus 6 times 25 squared is, sorry, 6 times 5 squared is 150. All right. I don't have to rewrite that middle term. And that is going to be minus WL to the fourth over 24 EI. 16, that's actually calculator time. Oh my goodness, I don't know where that's going. 16 minus 80, 64 plus 150, and it's going to give me 86 divided by 16 plus RBL over. You guys let me do that. See this? L cubed. I put it in red. That's the shame there. Shame. Over 3 EI. The red, I don't need the red, really. I don't need the red on the EI. Because I would have gotten those right. Oh. EI equals 0. So now let's move stuff across. RB is equal to, and I'm going to put a 3, and then the L cubed and the EI go away, because I'm just going to put down WL, and then I've still got a 24, and I can start to reduce that to 43 over 8. And now I can look at the 3 and the 24, and I can reduce that to being WL over 8 times 43 over 8. And that's going to give me WL times 43 64ths. Now, that probably won't ring a bell to you because you didn't just do problem 820 with integration, but I did. And I put it on the same page. I didn't tell you that. Maybe I did. But look at that. Look at that. That's from the other one. That's when we did it with integration. RB is 43/64 WL. Awesome. Now, I'm not going to make a straight comparison in terms of the level of difficulty. But I'll say this. This is everything I did when I did integration. You can't even see that. That's so fine because the... And then this down here is with cartoons. Maybe I have to use this. No, it doesn't help. That's yellow, so you can't see it. I think there's a lot more work when I did integration. I think. Both ways have work going on, and they've got a lot of calculations going on. They get me to the same spot. Once I've got RB, I can plug RB into this equation. Oh, I gotta get a better color. I can plug RB into that equation and solve for RA, and then I can solve, and then and I can put RB into that equation and solve for MA. So I've got it figured out. Wow, got to turn some stuff off. I've got it figured out. I don't know which way is easier. I think cartoons are a little bit, I don't know. I think maybe it's the word integration. It might just be the word integration. I don't know. Anyway, don't worry. There's more coming, but maybe not tonight. 8:30 on a Saturday? What am I? Oh, you guys can't see that. I got to get rid of my face. See? 8:30 on a Saturday. If you look in the corner, that's just ridiculous. All right. Don't worry. There's more to come. See you.